what blockchain is. Here's the agenda for today's lesson. First, we'll explain the world of SHA-256 hash, the critical element of the blockchain technology. We will demonstrate how it works and why it's so crucial. Next, we'll break down the basics of blockchain blocks, what they consist of, and how they're validated. We also touch on the mining process as well. We'll then move on the blockchain itself, looking at its structure, how it stays secure through the interconnection of blocks, and delve into the distributed nature of blockchains, explaining how multiple peers work together to maintain the integrity of the network. We'll stop by tokens as well. We'll explain what tokens are, how transactions work, and how we ensure they are valid. Then we'll introduce you to the concept of the Coinbase transaction, showing how the tokens are created and distributed. So for the blockchain demo, we will use this website, and you can try it by yourself for the deeper comprehension. Before we dive in, let's explore the essential component of blockchain technology known as SHA-256, Secure Hashing Algorithm 256. Please take a note of this term, as we will be discussing it throughout the session. The SHA-256 hash works like a digital data fingerprint. It appears as a sequence of random numbers, and no matter what data is put into a hash function, it generates unique hash. To demonstrate, let me enter any random text. As you can see, the length of the hash remains the same, as the result is obtained through the hashing algorithm or function used to process the input data. Additionally, every time the input is modified, the hash value changes. That is how hashing works. To give you a better idea, let me type "Hello World." You can see that the length remains constant, but the numbers are different. The hash starts with B94 and ends with DE9. If I cut and paste it again, the result is the same, with the hash starting with B94 and ending with DE9. This means that any data you put here will have a unique hash result. The hash function is so effective that regardless of the amount of information you input, whether it's a small piece of information or vast data set like a Library of Congress, the resulting hash will always have the same length. This makes it nearly impossible to predict or guess the hash value. Now let's talk about the most important parts of the blockchain, which is the block. A block has three parts: a block number, some data, and a nonce. You might be wondering what nonce is. A nonce is the number that is used to create a unique hash value for the block. Speaking of hash values, let me show you something. This is the hash value you might notice, and it starts with the 4 zeros. If I were to change the data and create a new hash value, you would see that it no longer starts with 4 zeros. This means that the block is not signed and it's not valid. For example, if I were entered any value, say BNB chain, you could see that the hash value is no longer valid. It no longer starts with 4 zeros. The box turns red because nonce number does not match the hash, does not have 4 zeros at the beginning. It's not valid and it's not signed block. So how do we create a valid hash value? We use a process called mining. This involves trying a different nonce values until we find a valid hash value that starts with 4 zeros. This process can take a lot of time and effort, which is why we have machines to do it for us. Then we click the mine button and the machine begins checking different nonce values until it finds the valid hash value. This ensures the security and, what's more important, immutability of the blockchain. Alright, the interesting part. Now let's look on the blockchain itself. It consists of several blocks. If we look here, we'll see block number 1, block number 2, block number 3, up to 5th block. The same applies to the nonce, data, and the previous block. This hash right here is linked to block number 2. You can see the previous hash here. So the block number 1 is linked to block number 2. And it has another hash value that will be linked to the next block, which is the block number 3, up to block number 5. Now what happens when I try to add some data to one of the blocks? If there is a change, say in the block number 4, from its initial empty state, the block will be invalid and the chain will be broken. The previous hash in block number 5 would not match the hash from block number 4, but not affecting the block number 3, number 2, and number 1. So this is the problem. And when it happens, I have to click the mine button. I have to mine this block number 4. Once it's mined, take a look at the hash. It starts with 4 zeros. This means that it has not been completed yet. It has to get to the block number 5. So this means that when one of the blocks is updated and its value changes, the entire blockchain must also be updated by hashing each of the blocks. This requires a lot of computing power, which is why we need powerful mining rigs. If the block number 5 is mined, it will be valid by matching the hash of the previous block. Now let's explore the distributed nature of a blockchain. A distributed blockchain is like a chain of blocks that exists on multiple computers known as peers. Each peer has an exact copy of the entire blockchain. For example, here's a peer A, peer B, and peer C. Each peer holds an identical copy of the blockchain. This distribution ensures that if any modifications occur, they can be quickly detected by comparing the hashes of the latest blocks. For example, if I change the block number 4 of peer B, it will affect this particular block, but won't affect the other blocks or peers. So let's mine block number 4 and block number 5, so both blocks will be valid and the whole chain will be valid. However, if we compare this hash in the block number 5 in peer B with block number 5 in peer A or peer C, we will see that they are not the same. This is because if someone tries to change block on one peer, its hash will no longer match with the others. This discrepancy immediately alerts the other peers that something is wrong. They will reject the altered block and maintain the original version as agreed upon by the majority. This democratic consensus mechanism prevents any single peer from manipulating the blockchain. It ensures that only valid and unchanged blocks are accepted and added to the chain. So this is how distributed blockchain works. Now let's introduce the concept of tokens on the blockchain. Let's take a look at them. Tokens have values in peer A, peer B, and peer C. Instead of data, we have transactions here. We have a block number, a nonce, a previous block hash, and a hash of this particular block. Here, inside, we have transactions, which means we want to send tokens from one person to another person on the network. Let's say we want to send 25 tokens to Bingley. It's sent from here, and now let's look at the hashing value to see if the results match. Comparing B and A, we can say that it is the same thing. Now let's try to change something inside transactions. Instead of 25, I change this value to 100. You can see that it's turning red. This is invalid, so I want to mine it, solve the problem, and make it green. When I click here, the problem is solved. It comes with an expected results starting with the 40. But again, we have to compare this with the other peers on the network. When we compare it, we see that the hash value does not match. So when we know that these two parameters are not the same, we need to use the hash value in peer B and peer C and compare it with other peers in the network. We can see that these two actually match, which means that these two are valid and this one will be excluded from the network. So here's how tokens work, sending tokens from one person to another person on the network. Let's explore the concept of the Coinbase transaction on the blockchain. Essentially, a Coinbase transaction involves the creation of the new tokens from a thin air, which are then assigned to a specific recipient. Let's call him Anders. This serves as a starting point of the blockchain. In the next block, another set of tokens is generated and given to Anders again. At this stage, there are no other transactions, so Anders is the sole holder of the tokens. As the blockchain progresses, transactions begin to occur. For example, let's say Anders wants to send 10 of his tokens to Sophie. Before doing so, he needs to check the previous Coinbase transaction, which gave him 100 tokens, to ensure that he has enough tokens, to send to Sophie. This follows the rule that no new tokens can be created out of thin air, providing transparency and the control over the currency. When we review entire blockchain, we can trace the flow of the tokens over the time. For example, if Jackson gives Alexa 2 tokens, we can verify if he actually had those tokens by checking the previous transactions. In this case, we can see that Emily gave 10 tokens to Jackson in a previous block, confirming that Jackson indeed has the tokens to transfer to Alexa. This is possible because each block points backwards to the previous one, allowing us to trace the history and the origin of any token on the blockchain. To summarize, a basic blockchain is like a shared permanent record that can be used to create a currency. Everyone who is part of the network has a copy of everything that is stored on the blockchain, and it's constantly being updated in real time, so everyone is on the same page. If anyone tries to mess with the blockchain, like by changing how much money was transferred, it won't work, because other copies of the blockchain will reject it. This is why blockchains are so good at handling money and other transactions. This is just a quick overview, but in part 2, we'll go into more detail about how transactions work. Thank you for listening, and see you on the next lecture.